Good evening, folks, and welcome to the Advent of Code C++ live stream. My name is Craig, and tonight, as we do every night during Advent of Code, we're going to be working through the night's puzzles in C++. Thank you for tuning in, whether you're watching the live stream on Twitch or you are watching the replay later on YouTube. If you're watching on Twitch, you can go to my channel profile. There you're going to find links to the YouTube channel that has all of the stream replays for all of the puzzles, plus the GitHub repo where we upload all of the code that we write. If you are watching on YouTube, just check the description right down there. You're going to find links to the Twitch channel for the live streams, and once again to that GitHub channel where we upload all of the code. So we are really in the home stretch right now. It is just a few minutes until day 23's puzzles unlock. And after that, there's just a couple more days after that. We have had a few pretty tricky puzzles the last few days. I would say that the theme of the especially tricky stuff this year appears to be like three-dimensional, like tricky three-dimensional geometry. There was that problem of, I think it was day 19 maybe, of finding all the sensors based on the beacons, and the sensors could be oriented any which way. And then last night we had another interesting geometry-related one where we had a really, really huge space, and we're turning on and off regions of cuboids in the reactor. And the regions were so big that, we couldn't keep track of every point individually, so we had to do, like, some solid geometry and figure out how, like, intersections and cutouts from different boxes in that three-dimensional space. So, yeah. The theme of the hard stuff this year definitely appears to be geometry. But we'll see what we get into tonight. We might have another real thinker. I haven't been totally stumped by any of these yet, but I've definitely been slowed down, especially in some of the hard geometry problems, to really have like a good think about something and figure out how to solve certain problems. But we'll see. You never know. I might hit a real stumper one of these last few days. Might need to take a step away and think about the problem some more. Or maybe not. Maybe we will just breeze through these. You never know. But we have about 2 minutes until tonight's puzzles drop. So I have already set up here just the bare bones skeleton of a solution program for day 23 here. You see we have this source code, just a main function that does nothing but return 0. And I've included the check and IO libraries that I use pretty much every night. These are libraries that I've written myself. They're up there in the GitHub repo along with all the puzzle solutions. Check we use to do assertions, and IO we use to read in and parse the puzzle input files. And it's handy just to have those pre-written so that we don't, rewrite them every day. I've also set up this build file, which tells the Bazel build system, which we are using, how to build the program, tells it the name of the program, what source code files to use, and what its library dependencies are. So once again, you see check and IO there. And I've already run the program here with this Bazel command, and we see that it builds successfully, it runs, and it does nothing as we expect, because the program's empty so far. So we've got less than a minute until tonight's puzzles unlock. We are delving deeper and deeper into the ocean, down into an ocean trench, in our search for the sleigh keys, as we unlock more and more of this ASCII art picture. Often, in previous years, when you solve all the puzzles, when you get all 50 stars, a lot of times, like, the ASCII art picture then starts to animate, and you see, like, other, cool new secrets in it. So over these next few days, we'll see what additional surprises show up in this ASCII art picture of the ocean. But for now, let's get into the new puzzle. Amphipod. A group of amphipods notice your fancy submarine and flag you down. What is an amphipod? Okay. Crustaceans. All right. Surely you can help us with the questions that stumped our best scientists. You understand a group of timid, stubborn amphipods live in a nearby burrow. Okay. 4 types of amphipods live there: amber, bronze, copper, and desert. Live in a burrow that consists of a hallway and 4 side rooms. The side rooms are initially full of amphipods and the hallways initially empty. Give you a diagram of the situation, including locations of each amphipod, A, B, C, or D, which is occupying an otherwise open space, walls, and open space. The amphipods would like a method to organize every amphipod into side rooms so that each side room contains one type of amphipod and the types are sorted A to D going left to right like this. Okay. They can move up, down, left, or right so long as they're moving into an unoccupied empty space. Okay. Interesting, interesting, interesting. Each type requires a different amount of energy to move one step. Okay, so this is kind of a pathfinding thing, but with multiple amphipods. So we have this geometric series of how much energy different amphipods take to move. They want to organize it in a way that requires the least total energy. However, because they are timid and stubborn, they have some extra rules. They'll never stop on the space immediately outside any room. They can move onto that space so long as they immediately continue moving. Okay. There's the 4 open spaces and hallway that are directly above. Okay, so they will not stop on that space. If they move there, they have to keep going. Amphipods will never move from the hallway into a room unless that room is their destination room, and that contains no amphipods which do not also have that room as their destination. If an amphipod's starting room is not its destination room, it can stay in that room until it leaves the room. Okay. Once an amphipod stops moving in the hallway, it will stay in that spot until it can move into a room. Once any amphipod starts moving, any other amphipods currently in the hallway are locked in place and will not move again until they can move fully into a room. Oh boy. Okay. So, lots of rules that we have to implement here for these moves. So, let's see. Bronze amphipod moves into the hallway. 1, 2, 3, 4. Copper moves over there. Desert guy moves up here. Wait, so where's the desert guy coming from? Okay, so he's good. Desert guy went 1, 2, 3 there, and then this bronze went 1, 2, 3 down. Left mode amphipod. Okay. Oh boy. Was the least energy required to organize the amphipods. Okay. Let's look at how our puzzle input looks and how big this problem actually is. And we'll get started. Let's look at day23.txt. Oh, well, this isn't bad. That's tiny. I shouldn't say that it's fully tiny, but like the size of the puzzle is the same size as the example. So the state space should not be so gigantic. Let's start thinking about how to represent the space. So first, we'll just have an enum called cell, which will represent something in the hallway. Well, I mean, honestly, we could just do this in string form, I guess, but let's see. I'm just looking at the rules again here. So they will never stop on the space. I mean, they can't. They can move into an adjacent empty space. They will never stop on the space immediately outside a room, but they can go through that space as long as they continue moving. They will never move from the hallway into a room unless that room is their destination room, and that room contains no amphipods which do not also have that room as their own destination. Okay. So we'll have this enum class cell here, and its values will be empty, A, B, C, and D. And then the configuration here, so we'll have, how wide is this? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, okay. So we'll have a struct to represent the state. We'll have (11) in the hallway. And then we will have stacks of 2 in each of the rooms. So we'll say no, we'll fill those in a minute, but we'll say room A, room B, room C, and then we will, write something that allows us to that implements the movement rules from this. So we've got our states here. We can write a parser for the initial state, but honestly, I'm going to hard code it, I think. Is there a constructor for this that will just, fill everything with k empty? I mean, it should be zeroed out anyway, but let me just check that. So we have kind of a pathfinding algorithm here between different states, and we can use A star for that. It's just to figure out, like, we need to follow the movement rules that were given to figure out what states are reachable from other states and how to evaluate their cost. But fundamentally, this is a pathfinding algorithm where the nodes are different legal states. So let's see here. And then, yeah, I'm going to hard code the stuff. We'll say that position 0 is the one next to the hallway, position 1 is the one below that. So okay. And we will, again, I'm kind of hard coding. I'm hard coding here. I will maybe go back and write a proper parser for this later. Actually, you know what? Now I'm seeing something here that we'll just say k initial state, which we'll hard code here and say dot hallway is all empty. Dot room A is B, then C. Dot room B is KA and KD. Room C is B, then D. I need to capitalize that. And finally, room D is C and A. Now, one thing that I notice about this is that none of the amphipoda are in the rooms that they're meant to be in at the end. So so let's see. Remembering, they will never, okay, amphipods will never stop on space immediately outside any room. They will never move from the hallway into a room unless that room is their destination and that room contains no amphipods which do not also have that room as their own destination. Okay. Once an amphipod stops moving in the hallway, it will stay in that spot until it can find a room. Okay. All right. So the next thing we need to do is figure out a way to expand the possible states from a given state and figure out, yeah, where things can go. So we're going to, well, so, we need to pair these actually. So I'm going to, so we'll say an int64t for the cost. We will call these successor states that we can, oh, that should be pair. Sorry, I meant to say pair. Pairs of those. So first thing we can do is we can scan the hallway for amphipoda that are in some spot in the hallway and see if we can move them into their destination room. So for just say hallway position equals 0. Hallway position is less than 11 plus plus hallway position. If the cell there is is empty, then there's nothing to move there, so we can ignore that and continue on. If otherwise, we will look at the destination and try and get there. So here, we'll just write a function here. Which will, for a cell, give the room position in front of it. So give the position in the hallway that is in front of the destination cell for that kind of amphipod. So if it's empty, well, it shouldn't be called with empty, so we're going to check fail there. If it is KA, then it is 0, 1, it's 2. If it's KB, then it is 4. C, it is 6. D, it is 8. Okay, so the destination is room position for that's the amphipod in that cell. And then we just need to calculate up the energy for it to move to that. So we'll say, oh, yeah. We'll also go ahead and set this up here. So, everything from the hallway position to the destination, including the destination itself, has to be clear in order for it to get there. So, first thing that we will do is say because remember, if an amphipod is in the hallway, it is in a given position in the hallway. It's frozen there until it can move all the way into its destination room. So if the hallway position is less than the destination position, then we will check all the positions in that range. So we'll say for going to go less than or equal to destination because the destination itself has to be clear. If there's any other amphipoda in the way, then the path is not clear, and we can stop checking. But if the whole path I mean, actually, like, well, yeah, I mean, we can do this either way, but if not path clear, then continue on to the next iteration of the outer loop. Actually, I'm going to put that out here because we'll just do something very similar for the other direction of comparison. Else, if hallway, well, else the hallway position better be greater than the destination, otherwise it would have gone in there and it would have been an illegal position. So we'll just check there that hallway position is greater than destination. And we will have a similar loop here, except just going in the other direction. Okay, so then down here, if the path is not clear, then we return false. Not return false. We just continue. Sorry, we just continue on to the next version of the outer loop, looking for other amphipoda that are in the hallway that can move. Okay. But if there is a clear path to the destination, the next thing that we need to check is that we have the next thing that we need to check is that the destination room doesn't contain any other types of amphipoda. So we'll just write a little helper here. We can, make it private, but call it destination room and this will just return a reference to the destination room that we want to check, so that we can make the successor states function more generic when we're checking that destination room. So if the cell is empty, then we've done something wrong. Otherwise, we have these for the other rooms, and I'm just going to copy and paste to speed this up a little bit and fill in B, B, C, C, D, D. Okay. destination room for well, actually, well, you know, now that I think about it here, I'm going to go ahead and say just bind a reference to source cell here. Well, yeah, I mean, we're going to be making a change, but yeah. Whew boy. I'm going to make a similar mutable version of this that we're going to need when we're actually constructing that successor state. But we'll say destination room for source cell there, and I'm going to go ahead and replace these with source cell for readability here. Well, so it can only move into it. They'll never stop on the space immediately outside of the room. So if the front space is not empty, then there's nothing that can be done there. So if the front space in the room is empty, can't do anything. Otherwise, if the bottom cell there is empty, then the amphipod is going to have to move all the way down. I mean, we could do a separate step where it just goes into the top, but it would have to move further down for another amphipod to get in there of the same type to get in there anyway. So we're just going to force it to go all the way down. So at this point, oh yeah, const int, we'll say hallway path length is the absolute value of hallway position minus destination. And then we'll have 2 more times this hallway path length. So we'll say make a copy of this successor dot hallway at that hallway position is going to be empty after this. And then successor dot destination room at the destination room for the actual thing at position 1 is going to equal that new source cell, and then the cost is going to equal hallway path length plus 2 for the 2 steps into the room times the cost for a given type. So we'll go ahead and write that function. We'll say call that energy. And once again, I'm actually going to steal the skeleton of the switch statement and just write in the proper values. So those are going to be, if I recall correctly, 1, 10, 100, 1,000. But yes, 1, 10, 100, 1,000. So 1, 10, 100, 1,000. Geometric progression. So it's going to be that many steps times energy for that type. And then successors dot in place back. That successor and that cost. Okie dokie. So the other possibility here is that that bottom destination cell is not empty, but it contains another. Is that a problem? Why is that a problem? Expression result. Else if, sorry. But it contains another amphipod of the same type. So in that case, we would just move into 0. So we'll similarly construct something here, but it's going to be source cell 0 with that new one, and hallway path length plus 1 times energy, and we'll put that in. Otherwise, we can't actually move there, and we don't add anything. So this whole thing here is for moving amphipods to final rooms. The other thing that we need to consider for possible successor states is moving amphipods out of rooms into the hallway. So I guess we'll write this for well, okay. I'm going to just write this for room A, and then we'll generalize it to the other rooms, I think. Or, you'll see. We'll just go through A, B, C, and D here, and not what I wanted. Keep accidentally copying the whole line instead of pasting. Curse these metal hands. Okay. So, it's not really destination room. I mean, we'll call it actually the source room, but yeah. I think we'll say if if the top is already the desired type for a room, then there's nothing to do. If the top is not empty, then we can try and move it. Else, if that first one is 0 and if the bottom cell is the correct room type, then we're going to leave it there. And we can continue. Otherwise, source, okay. Okay. So we have figured out, so it's going to be the initial room position plus 1 is going to be the number of steps to get to the spot immediately outside the room. And I realize now that, you know, we could have an amphipod move all of the way from one room to the other as long as things are all clear outside. But I think that there are also a limited number of intermediate states where they just stop at some cell in the hallway in between and keep on going. And then those are all going to have the same cost. So I'm not going to worry especially about that. I'm only going to consider ending positions, which are a valid position in the hallway. So we'll say here, if hallway at that starting room position is not empty, well, that should never actually happen. I think, because there shouldn't be anything stopping. Yeah, amphipods will never stop on the space immediately outside of a room. So we'll actually just check that is the case. And then, so we will go left, and we will calculate out spaces as far left and right as we can go. So we'll say for int final hallway position is that starting room position. And so we'll go down to 0 and up to 10 in either direction. And that should not be starting room position. That should be final hallway position. Okay. If there is something standing in the way at the hallway there, at that final hallway position, then we can't go any further in that direction. So we'll go ahead and break out of this loop. If that is empty, well, so if it is one of the special positions 2, 4, 6, or 8, I'm just going to hard code these in here, but one of the positions in front of a room, we can't stop there. So we will continue on to the next thing to try. Okay. Otherwise, yeah, it's a valid position we can actually end up in. So we will do state successor, do a copy of this state. We will put, we will empty out the cell that we came from in the source room, and we will put into the cell in the hallway what we had initially. So and we need to calculate the cost. So that is going to be the initial room position plus 1 to get out into the hallway, plus the starting room position minus the final hallway position in distance, and then times energy for that type of amphipod. And then we can go ahead and put that in the list of successors. Moving probably actually isn't doing anything here, because since we're using arrays for all of the containers, it's just going to be mem copying anyway, but it's a good general practice to be in, is to use move when moving entities around in containers. Okay, so that's the loop that we do for going to the left, and we can do something very similar for going to the right. I'm going to copy paste right now. I may clean this up later on, but yeah, we can't actually let it be at the starting room position to start with, because well, that'll just be one of the illegal positions, and we'll continue, so it doesn't really matter. But we'll have final hallway position is less than 11, and then plus plus. So this stuff is all the same, except that we will change and do final hallway position minus starting room position instead of the other way around to calculate the distance in the hallway. So I think that now we have something to calculate all of our successors and their costs. So I guess another question is, do we want to memoize certain successor states? I don't know. But next thing that we need to do, the one more thing that we need to do for state is write an equality operator and make it hashable in order to use these states with the generic implementation of the A-star search algorithm that I've already written. So we'll write an equality operator and that just will compare all the fields. Okay. Hallway A, B, C, and D compared. And then we just need to make this hashable. So we'll say friend h absol hash value. H is the state of the hash, and then const state and state. Turn h combine, move the state, and then we just do all the important fields in here. Okay, so now it's hashable. We have this initial state. Actually, we needed to also specify the goal state. And the goal state, you know, we really truly can hard code because it's always the same. It's going to be an empty hallway and then everything nicely sorted. So it's going to be A's in room A, B's in room B, C's in room C, and D's in room D. Okay, now I'm going to include my nice generic A* library, and we will use that to find a path. So this we can do auto path equals OC 2021 A*. So the start node is K initial state. Should be goal, not ghoul. K goal state. The adjacency function, we can say const see, this makes me want to maybe like memoize some of this, but I don't know. I don't know if it's worth it. Yeah, maybe it is. Yeah, I'm going to do that. So we will intentionally ignore this field for equality and hashing, but when successor states is called, yeah. Yeah, that's... Sure. We're going to make it a private field here. And you know, now we're getting to the point where, you know, this is really a class. It really should be a class, but we'll clean that up later. But what I'm going to do here is I'm going to, well, recursively defined. It's going to be a mess. I don't know. We'll do this the slow way first, where we're going to be recomputing successor states. Don't like this. So the way that I've written this A* thing is that we need to provide it with a separate function to get adjacent states from a given state, and to evaluate the cost for edges between for edges between states. And the way that this successor states is written is that it's not written that way. But you know what I'm going to do here is I'm going to do the memoization here because I just feel like that's good for performance. Yeah. And then we will write these into some Lambda captures. So we'll just say capture those by reference. Oh, yeah, equals. And so we'll try and find that state in successor, that start state in successors. If we do find it, we will return a vector of state for successors. We should probably be sure and try and return it by value. So I'm gonna, and actually copy it, just in case the A star search tries to do some modifications. So we find it, we're all good. Otherwise, we need to calculate it. So we will then say state and cost. We just get from start dot successor states. Basically unzip this. Actually, the easier way to do this is like that. And we will also put it in the, we'll also put stuff in the cost map. So, well, so first things first, we will check that that insertion was successful, and then we will update the cost map as well. Although actually, well, yeah. So instead of moving that, we're gonna want to return that vector of state. So I'm gonna not move that. But since we've calculated the costs right now, we're gonna put the costs in. So we're gonna say for const auto and, or actually just, you can just say for auto state cost. Instead of just calling this cost, I'm going to call it edge costs, be a little more specific in my naming. But we'll do that in looping through state and cost. And edge costs dot in place. Or, yeah, it should be so be start and state are the pair key there, and then they map to costs, and that should be new and be in place there. And then Finally, we will return that vector of states. Okay. So get adjacent the first time get adjacent is called, it memoizes stuff in these maps so that we're not constantly recalculating successor states a bunch of times for a given state. It may be a premature optimization, but we will find out. Don't know why it wants to indent that so far, but we'll come back to that in a second. So get cost only needs to capture the edge costs, because I happen to know that get adjacent will always be called before get cost, for a given pair. So that should give us int64t. Oh, that's why. No semicolons. That's why I was not enjoying that. But get cost, we should be able to just do edge costs dot find from start to next. Can't be edge cost dot end. And I realize that, of course, we actually need to check this as well. So just say if known it does not equal successor dot end. It's already known for this. There we go. Second. Okay. So now we can provide it with our get adjacent and get cost. We should check that it actually found a path that has value, and then we can write out the cost of that value. The cost of that path, rather. Okay, so I think we have our solution here. We need to include a star and flat hash map as additional dependencies. So gonna just do some copy and pasting, flat hash map there, and a star. And let's go ahead and try and run our program and see if it breaks. Yes, okay. It does break because a check failed. Let's see what that check is. Line 110. Okay. So we have somehow wound up with a situation where the hallway in front of a room is not empty. Oh, you know what? These are off by... No, those aren't off by 1. Never mind. I thought for a moment that they might be, but they are not. Just putting a little debugging statement in here. we're generating these. Let's go ahead and see. Wow, we did not even get that far. So did we not initialize those things properly? I mean, we're failing something pretty basic pretty early here. Oh no, it has to be empty. It doesn't have to not be empty. It has to be empty. Duh. Backwards of what the comparison should have been there. Okay, now we get up to another problem. We try to compute energy for an empty cell. Count that there, but we'll say you put comments in here. No, oh, that's actually hallway to room. Um, see where it actually fails there. Okay, so we calculate a lot of left and right energy possibilities here before it actually decides to really be mean to us. Let's see here. this I actually suspect may be incorrect. I may have been careless here. So let's see here. The position in the initial room that we are moving from, if it is... Now, if it's not empty, then we're moving from 0. If 0 is empty, then if the bottom one is already in the correct position, we skip, but otherwise we're moving from 1. Okay. Let's spit out some additional information here. We'll say got our initial room position, which is important to know. Room position, I don't know how much this is actually going to be helpful, but let's just print out some of that for now and see if it gets us any farther in debugging. Okay, so the bottom of D, of room D, is where we're working from. And oh, okay. If the bottom is empty, there's nothing to remove from, obviously. So that's one thing that we forgot to check, is if the bottom of a room is empty, there's nothing to do with that. So that should be all we need. I'm going to take out some of these debugging statements because otherwise it is going to get super spammy. But yeah, obviously we can't move from an empty bottom cell either. Okie dokie. Okay. 14,510 is the total energy that it has for our version of the problem. Let's see if that's correct or if we made some other mistake. Hey, amazingly we got it right. Okay, part 2. As you prepare to give them your solution, you notice that the diagram they hand you is actually folded up. As you unfold it, you discover an extra part of the diagram. But for the first and second lines of text that contain amphipod starting positions, insert the following lines. Okay. So we have to expand to an even bigger problem. Well, A star, don't fail me now. I hope. So we're going to go... So first thing I'm going to do is just go ahead and make a commit with the part 1 solutions. And then we have to basically expand. So everything that we were doing with you know, rooms 2 deep, we have to expand to do 4 deep. So first thing I'm going to do is just copy my part 1 solution and use that to start with part 2. Okay. And then I will also copy it in the build file here because it's going to start with all the same dependencies. Okay. Part 2. So energy is the same. This is the same. These room sizes now go up to 4. Actually, I'm going to go ahead and say, I'm going to generalize this and say const x for k room size, k room size equals 4. And maybe change the things that were hard-coded to just look at 2 spots to actually be loop-based so that they are more general. Okay. So this I'm going to generalize and say well, going to write another routine that says and this is going to be an optional because there won't always be a free cell in a given destination room. So let's see. For positions in the room, if a given room position is empty, then we just continue with the loop. If it is not empty, then for otherwise, we got to check the rest of the cells to make sure that they are all the correct target type. So we will return null opt to indicate no answer if we find any in the bottom of the room that are not the right type, because we can't move anything on top of them. But if we get through all of those, then if pos is greater than 0, return pos minus 1. Well, so if position is 0, all right, if it's empty, we continue. If it's non-empty and it's the first position, then we return null opt, the room's full up. So then we can just return pos minus 1 here. And if we get through everything and everything is empty, then we return k room size minus 1, because we can go all the way down to the bottom there. So going back up to our successor states computation here, we've got our destination. But actually, what we really need is to get that from, we called it free cell and destination room. And if there is none, then we have to go on searching because we can't actually enter that room. But if we do successfully enter the room, then we can start working with one of these. So we empty the hallway position, and we put it in the right destination room position, and it's going to be +1 plus destination room position to enter the room and go however far down it needs to go. And that should be it for entering a room. Now, moving from rooms into the hallway, this is another one where we need to change things. So we look at a given source room, and so we'll just say realize this destination, it should be destination. There we go. But the way that I'm going to do this now is have another function that will be find movable from room. And I mean, this isn't exactly right, but basically, so for 0, position is less than k room size, plus position. If that top cell is empty, we keep on going, looking at cells further down. If the cell that we are looking at is I'm realizing now that some of these, like the interpolated things, the second row, like B is correct, but that B still has to move out of the way, I realize. Yeah, so like looking back at the puzzle here, I realize another added wrinkle of complexity here is that you see that, like, this does add a B that is in the correct room but has a D beneath it, so that B has to move out of the way to let the D in. So that's to let the, or rather that B has to move out of the way to let the D out and find other Bs. So instead of just seeing if this is right and stopping there, we will do for. We'll look at the bottom here. So, well, actually, first thing we'll do is, obviously, if it's not if the value there is not the right value for the room, it can be moved. So otherwise, if there's anything below that position, that is not right, then we will still consider it movable from the room. Okay. So if so we can still move something from its proper destination room in order to let something else out. But if we go through all of these, well, so if we get down here, then you should return null opt, because the value at the position is going to be the proper cell, and everything below it was also proper cells. So there's nothing to move out of this room. Like this room, at least the bottom part of this room, the filled up part, is already in the desired goal state. The next thing we need to, and then if we go through all of them, and either they were all empty, yeah. Go through all of them and they were all empty, there's nothing that can be returned either, so we'll do null opt here as well. Okay, so we have find movable from room now. I'm sorry, I just realized I was on the wrong screen this whole time, so while I was narrating that, but this find movable from room is what we just wrote. So we are going to look through, I need to remember to keep on updating this, what screen I'm casting properly. But find movable from room, we're just going to find, a particular destination room. We're going to look through the positions in it. If they're empty, we keep on going. If they are different than the desired cell, we can definitely move from that. If they are the desired type, but there are other wrong types beneath it, then we can definitely move it out because we need to let other things out. Otherwise, here, the bottom part is all full with what we want in that cell, or here the whole thing is empty. So we'll go up, and then we can say find movable from room there. Oh, sorry. That should be an optional. And if we didn't actually find anything, if has value, then we will continue, because there's nothing that we can remove from that room in this state. Does source room stuff matter? I mean, sure, we can say. This stuff can go away, because that's all handled by the function now. Look at all these different possible final hallway positions. Destination room. Got our energy there. I'm moving a little quickly, but I think this all still makes proper sense. Okay. Do a quick search for literal 2s. Fine. Okay. So now we need to change the way that our initial and desired states look to be 4 deep. So the desired state is easy enough. The initial state, we're going to put 2 Ds in the middle there. Again, you know, once I'm actually done with the hard part of the solution, I'll probably go back and, you know, make this programmatic instead of hard coding it. But this is what you get to see for now. So that's it. Well, no, that's not going to be DD. That is going to be CB in there. Then we are going to have BA. And AC. Okay. Format everything nicely. Still got an error somewhere. Where do you not like that? One place where we didn't properly dereference initial room pos there. There we go. Okay. Question is, will this run in a reasonable amount of time still? Let's find out. Running part 2. If this takes too long, okay. It thinks it's unreachable. Okay. Well, that's a problem, doesn't it? Oh, these should have been D's. Oh no, it's A B. Oh, we wrote our we wrote our goal state wrong, folks. That's why copy pasting always gets you in trouble. It didn't take that long to enumerate the search space and find out it couldn't get there, though, which bodes well. Okay, 49,180 is the answer for this new modified version of the puzzle. Let's see if that's actually correct. All right, and 275. That is our best result so far on any star this year. I feel really good about that. Okay, so I I think the first part, we were maybe slowed down a little bit, but it gave us a really good foundation for the second part. Oh, first part. Oh, look at this. We were 1,000 even on the first part, and 275 on the second part, which is our best result so far this year. So definitely feel great about that. Um, let's talk a little bit more about this problem, just kind of sum up things. Um, I think a really important thing to realize about this problem is that it's a pathfinding problem, and you can kind of think about that. Obviously, well, yeah, we're routing all of these little amphipoda animals to the rooms that they want to be in, but really, it's a pathfinding problem between different states of this relatively small state space, um, where all the amphipoda can be in the hallways or the destination rooms, and realizing that you can get from one state to another. There are rules about which states you can go to, like that are composed of where the amphipoda can move among the rooms, and then you just have to figure out what different states can you get to by moving individual amphipoda from one state to another, and how much does it cost to get there. And if you have that function of what's reachable and how much does it cost to get there, then you have everything you need to use a pathfinding algorithm like A star. And we already had this A star implementation that we had used on a previous day to do pathfinding, I think through like the danger zone of the lava vents or something. I forget the exact day. But, I had already written this and separated it into a library, so I didn't need to write A star again. I just needed to write the functions that plug stuff into A star. So how do we find adjacent? How do we find costs? And I chose to write these. Now, we could have written that get adjacent and get cost in such a way that every time we call them, we call successor states here. And that would have worked, but it would have been recomputing successor states a lot. So I chose to, trade a little time for space, or space for time, rather, and memoize these by saying, we'll only compute the successors for a given state once and their edge cost once. And then we will just go back and look them up again the next time the algorithm asks us to find that. And I think that probably sped things up significantly, such that, we found the solution in only a few seconds. So yeah, this was a pathfinding problem disguised as another pathfinding problem. But yeah, it was pretty cool. I enjoyed this one. And now, our second part solution really is, it's constant in the program, but it really is parameterized in the size of the rooms, this K room size here. We could alter this to any number, and we could still solve puzzles like this. So I think what I'm going to do is I'm going to end the stream pretty soon here. I'll probably clean this up a little bit to be able to actually parse, representations of room from the input instead of just hard coding my particular puzzle inputs. But yeah, this was pretty cool. Pathfinding disguised as pathfinding. So I hope you found this interesting. I hope you had a good time on the stream with me tonight. I certainly had a good time. It was pretty exciting to get our best leaderboard position of the year so far, at least on part 2, on that gold star. Thank you very much for watching, everyone. If you are watching the live stream on Twitch, you can check my channel description. There you will find links to my YouTube channel, which has replays of all of these sessions, plus a link to the GitHub repo where I upload all the code that we write. If, on the other hand, you're watching this later on YouTube, just check the video description right down there, and you are going to find links to the Twitch channel for those live streams, and once again to the GitHub repo where all of the code lives. Thank you very much for tuning in. Hope you had fun tonight, and I hope to see you again tomorrow night as we close in on the final couple of days of Advent of Code. Have a good one, Submariners. Bye-bye.